Okay guys, we're going to pick up where we left off talking about Taylor and Maclaurin series. And I want to point out that these series, which take this form in general, produce a series that approximates the function if you only use some of the terms. If you use all of them, it is a formula. So some of these formulas allow us to do logarithm, tangents, things of the sort, but it has an interval of convergence. So first off, the interval of convergence can only be so big when functions have difficulties. For example, the Taylor series of the function 1 over 1 minus x well, if you were to the left of here, say you did the Maclaurin series, it only can be good from minus 1 to 1, even though the function exists in more places. Let's take the square root function. The square root function doesn't exist over here. So your interval can be never bigger than an interval that includes 0. So some of these Taylor series have to be very limited in their uses. Same thing with a Maclaurin series. I mean, we can't even do a Maclaurin series for the square root because everything gets messed up once you get past the first derivative, which things are now in the denominator. So Maclaurin series for the square root of x is really bad. But what do we use them for? This is the important thing. We use them to be able to calculate these functions. As an example, the sine of x has a Taylor series and Maclaurin series, which is x minus x cubed over 6 plus x to the 5th over 5 factorial. Goes on forever. And let's suppose we take the first couple of Taylor series, the Taylor polynomials. T1 is x. It's not a very good approximation of the sine. It gets separated from it very quickly. The third Taylor polynomial is x minus x cubed over 6. It's a little bit better. It looks like this, and it's closer to the sine of x. The more and more of these polynomials you graph, the more and more of the sine it gets close to. But how do you use them? Well, how you use them is first to figure out how good they are. And Taylor's theorem includes a statement about the goodness, and that is the following. The remainder of the nth Taylor polynomial is bounded by the maximum of the function on some interval over n plus 1 factorial times x minus a to the n plus 1 on an interval. This interval, first off, your series is centered at a, so you've got a minus d up to a plus d. If you have some interval, and this is contained inside the interval of convergence, then how good is it on this interval? Well, it's the largest value of that power divided by the n plus 1 factorial, and m is the max of the nth plus 1 derivative on that interval. So let me show you an example of how this calculation can be done. So we're going to take the sine of x, and we're going to approximate it by x minus x cubed over 3. This is the third Taylor polynomial. So what it's missing is the remainder of the third Taylor polynomial. And so the remainder of the third Taylor polynomial is less than the max of the fourth derivative. Now, since it's being done at 0, this will be less than x to the 4th over 4 factorial on whatever interval we choose to be using it. So let's just decide that when we look at the sine wave, that if we did, let's say, from minus pi to pi, we'd have all the sine values everywhere. And let's find out how good this polynomial is. And it's bad out here, but it's only a cubic polynomial. So let's choose to evaluate it on this interval. If we pick a huge interval, it'll be really bad on the other parts. We only need so much. Well, first off, we know that every derivative of sine is a sine or a cosine, and its max is always going to be 1. So this is very easily 1 times. Now the function x to the fourth looks something like this. On from minus pi to pi, the highest value it has is pi to the fourth. And if we take out our calculator and calculate that, this is approximately number 4.0. So it says that in this interval, this is not a great approximation to the sine wave. But I'm going to graph it anyway. So I'm going to take my calculator, go to y equals, and I'm put in sine of x. I'm going to put in x minus x cubed over 6. The window I'm going to do from minus 3.16 to 3.16. And I'm going to put the height y from minus 5 to 5. And I graph it. And here's what I get. I see the sine wave, and I see that, wow, it's really accurate in there. It's only getting bad out there, and it's actually not as bad as it says. It only seems to be off by about most 2. In other words, this is a theoretical bound. It's actually much more accurate than that, but it's still not very good out there. Well, what would happen if we decided to go a little bit further? Let's write down an approximation for sine of x as x minus x cubed over 6 plus x to the fifth over 5 factorial. And let's go all the way up to, how far should I go? Let's go to the 9th. Minus x to the 7 over 7 factorial plus x to the 9th over 9 factorial. This is a 9th degree polynomial. Let's approximate sine x on only from minus pi to pi again. And I'm going to calculate what R10 would be. Well, the maximum of the 11th derivative of sine, again, is a cosine or a sine, on minus pi to pi, and that's bounded by 1. X minus 0 to the 11th over 11 factorial. But now x is only varying between minus pi and pi, so the biggest this will be is pi to the 11th over 11 factorial. So I'm going to put that in my calculator. Oh, sorry, this is supposed to be a 9 and a 10 and a 10. Sorry. I'm at the 9th Taylor polynomial, and the 9th Taylor polynomial is bounded by the 10th derivative rule. And this value, 0.0249 or 0.025, it says that the sine is really accurate to 1, maybe 2 decimal places, theoretically. Well, it turns out if you actually take T9 minus the sine of x on minus pi to pi, oops, absolute value, it's much better than that. It's actually less than or equal to 0.0007. It's really accurate. Now, if you want 10, 20 places of accuracy, you just need to make these numbers large enough so that gets smaller and you get the accuracy you want. So if you want sine to be accurate to, let's say, 30 decimal places, you might just need pi to the 45th over 45 factorial to get 0.00000 to get the accuracy you want. So what's kind of cool about this is we can now do trigonometric functions, and we can do arc trigonometric functions, and we can figure out these values. And what's neat is there's a few of these values that we can now numerically calculate. For example, maybe we want to understand what pi might be equal to. Or maybe you want to know what the square root of 37 is accurately. So let's do one. Let's do this one. Let's figure out the square root of 37. So I'm going to start with f of x equals the square root of x. And there happens to be a square root I know really close to 37, namely x equals 36. So I'm going to pick around x equals 36 because the square root of 36 equals 6. So I'm going to do x minus 6 to the n over n factorial, the nth derivative of x evaluated at 6, and add it all up from 0 to infinity. So I need lots of derivatives of this function. Well, f of x equals x to the 1/2. F prime of x equals 1/2 x to the minus 1/2. F double prime of x equals minus 1/2 x to the minus 3/2. F triple prime of x equals minus minus be plus 3/2 1/2 x to the minus 5/2. I think I'm going to stop there. Now I'm going to evaluate each of these at 6. Well, f of 6 is square root of, 36. 36 is the square root of 36 is 6. Then f prime of 36, oh yeah, I should have written 36 there and 36 there. It's the x value I'm centering at. Sorry about that. Here's the point, 36, 6, and I'm going to evaluate how good my Taylor polynomial is going to be on some specific interval around 36. So f prime of 36 is 1 over 2 root 36, which is 1/12. F double prime of 36 is 1/4, 1 over square root of 36 cubed. So that would be 6 cubed. And this f triple prime of 36 will be 3 over 8, 6 to the 5th. All right, so I'm going to get these to create my Taylor polynomial. So here we go. I'm going to do T3. It is 6 plus, that's the first one, 1/12 over 1 factorial x minus 36 to the first, plus, let's see, this is, what is 36 cubed? Let's do that. 6 cubed. 216 times 4 be 1 over 864 x minus 36 squared over 2 factorial. Let's just stop there. This is getting kind of crazy. So here's a quadratic that is probably someplace right in there. And let's figure out what it says for the square root of 37. 6 plus 1/12 of 1 is 1/864 times 1 over 2. I'm going to calculate that number. 6 plus 1 divided by 12 plus 1 divided by 2 times 864. And I'm going to get 6.08391. So I wonder what our calculator says for the square root of 37. Now it's using a Taylor polynomial, but I'm sure this Taylor polynomial is much, much longer than the one we just used. And so our calculator says that the square root 37 is 6.0827. So looks like we were off by 11 ten-thousandths, an error of 11 ten-thousandths. So wasn't terribly accurate, but I just used a quadratic. This is how we use these series, and we can come up with some great values. And by the way, this number e that you knew a long time ago, turns out the Taylor series for Maclaurin series for e is x to the n over n factorial, n equals 0 to infinity. So if you plug in 1, this is 1 plus 1 plus 1 squared over 2 plus 1 cubed over 3 factorial plus 1 cubed over 4 factorial. And you can just cut this off anywhere you like. For example, let's cut it off there and see what our approximation for e is. 2 plus 0.5 plus 1/6 is 2.666 forever. And what our calculator says for a value of e second. It says it's 2.718, so we see I have an error here, but I cut it off very early. What's really interesting is ln x. Turns out if you pick some value near what you want to do and calculate a Taylor series for that, you can get values for ln x, square root of x, sine of x, tangent of x, cosine of x, secant of x, e to the x, all those buttons on your calculator. You can by hand calculate a Taylor series and then calculate with them. It's necessary for many of the trigonometric ones that you have to put in radians, and so you have to be able to express something in radians, and that might mean if you wanted to put in 12 degrees, you have to know the number pi, but you have a method by approximating pi as well. So when you use these series, you have the ability to know values that you've never known before. So some of the more interesting series, we should actually just state that we know. So if you look on page 768, we have a list of the geometric, the exponential, the sine, the cosine, the tangent, the arctangent, log of 1 plus x. They just did it. That's an easier one to calculate. And they also have something called the binomial, 1 plus x to the k. We have a series for that for any k that you would like to pick, and it's infinitely long so that you can calculate kth power of things. Well, what's really nice about this is that now you have reached the point where very difficult calculations can be approximated with operations, addition, subtraction, and multiplication that are quite easy. About the only way to really extend this is to extend it to functions that are really complicated, or you might not want to take their derivatives. So here's the last thought for Calc 2. Suppose somebody said, I want you to do e to the x divided by sine of x, or you would do e to the x times cosine of x. You want to do series for these. Well, there's a little trick called infinite algebra. Let me do this one. What's e to the x times cosine of x? Well, I'll just write down the series for e to the x. But then I'll write down the series for cosine, which is 1 minus x squared over 2 plus x to the 4th over 4 factorial. Now I just want you to imagine that you did an infinite number of multiplications. Let's do this one first. 1 minus x squared over 2 plus x to the 4th over 4 factorial. And then plus x minus x cubed over 2 plus x to the 5th over 4 factorial. And now I'm going to do the next one. Plus x squared over 2 minus x to the 4th over 4 factorial. And it turns out sometimes some of these cancel, and what you can do is you can get a series. It may be an odd type looking series, but it's predictable. I think this one starts with 1 plus x, and then I think it's minus x cubed over 2, and I think the next one's minus x to the 5th over 4 factorial, but there's 2 of them, and then there's a plus plus. It's an odd looking series, but just imagine multiplying these out, stacking them all up, and then adding them up. The further out you go here, the larger the other rows get. So once again, if you want a series that's 12 long, well, then make sure you go out here 12 terms and they've been multiplied, and you just add up the front 12, and you'll have an approximation series for that one. Now the weird one is to do division, but it's just long division of polynomials, except they're infinitely long. So the fun one, and everyone should do this one, just do it once. We know that the sine of x as a Maclaurin series is pretty simple. It's the odd powers with an alternating series with factorials. And we know that the cosine is the even powers so the tangent of x, if you want to figure it out, you can take x minus x cubed over 3 plus x to the 5th over 5 factorial, divided by x squared over 2 factorial plus x to the 4th over 4 factorial, and you set it up in long division form. You put them in order. Ask how many times does 1 go into x? Well, it goes in x times. Then x times this is x. Then x times this will be x cubed over 2 factorial with a minus. The next time the x will be plus x to the, that'll be a 5th factorial over 4 factorial. And then you'll subtract these, and so you'll get an x to the 3rd over, that's a 2, 6 minus, see, 1, 6 minus a half will be a 3rd. Even power, and then you do it again, and you can get a series for tangent of x. I believe the next term is 1/3 x cubed is what's required. Oh, yeah, that one. You need to cancel that one. So you can get a Taylor series for tangent of x by having a previous Taylor series for sine and cosine. All right, and that's the course, guys. Have a good day.